Welcome. In this lecture, we start new chapter, so that is infinite series. Infinite series. Okay, so what is the infinite series? So what is the definition of infinite series? Definition. Okay, let un be a sequence of real numbers then the expression u1 plus u2 plus u3 and so on un up to infinity is called an infinite series. Is called an infinite series. Okay, so it is denoted by, so this series, it is denoted by summation un as n is equal to 0 to infinity or 1 to infinity, or simply summation un. So this is the notation for the infinite series. So for example here, let us take a sequence 1 upon n is the sequence here. So what is the sequence here? We study this, what is the sequence in the last series of the sequence. So what is the sequence 1 upon n? So that is 1, 1/2, 1/3 and so on. So 1 by n and so on. So this is a sequence. So we make a series by using this sequence. So what is a series? So that is a series is summation un. N is equal to 1 to infinity is equal to. So this is the addition of the terms in a sequence. So that is a series. Simply 1 plus 1/2 plus 1/3 and so on. 1 upon n. Infinity up to infinity. Okay, so this is the series here. So this is a sequence and this is a series. So what is the convergence of this infinite series? So we understand here what is the definition of infinite series. Very simple definition. So we study what is the sequence and convergence of the sequence. By using sequence, we create here the infinite series. And the next part is what is the convergence of the infinite series here. Okay. So what is the partial sum? Partial sum of the series. Partial sum of the series. Okay. So what is the partial sum? So this is the series. So this is series summation un. So what is the partial sum? Let un be a series, infinite be an infinite series. Infinite series. Okay. Suppose we write. Suppose. So what is suppose we write here. We write. What is Sn? Sn is what? Sn is sum of first n terms in the series. So that is first n term u1, u2, u3, un. So u1, u2, u3 plus un. So this is the partial sum of the first n term in this series. That means what is S1? S1 is what? Only one term is there, U1. What is S2? So that is U1 plus U2. What is S3? So that is U1 plus U2 plus U3. So what is Sn and so on? What is Sn? Sn is equal to U1 plus U2 plus and so on up to Un. So this is the partial sum. So there are one term, there are two terms, three terms and n terms. So this is called partial sum. So this is called partial sum. Partial sums. Okay? Very simple here. Partial sums. So what is the definition of convergence of the series here? So definition is what? If the sequence Sn converges to a real number, converges to a real number S. Real number S. So Sn is a sequence having limit S. So this is a sequence Sn converges to S. Then we say that the series Un also converges to S. We say that the series Un also converges to S. Okay. So this is a definition of infinite series, and what is the convergence of infinite series. So we make here this sequence Sn of partial sum. So what is the sequence Sn? Sequence Sn is what? So this is sequence S1, then S2, then Sn, okay, and so on. Okay, so what is S1? S1 is this, S2 is this, Sn is this. Okay, so we make a sequence Sn and find out the limit of that sequence Sn. If the limit is yes, then this limit of the series is also yes. Hence, the sequence Sn converges to yes, then the series Un, summation Un is also converges to yes. Okay, so this is a definition. So we take here an example of the convergence of the series. Very simple example. Let us take example. So show that the series, example, show that the series summation 1 upon n into n plus 1 is convergent. Solution. Okay. Show that the series summation 1 upon n into n plus 1 is convergent. Okay. Okay. Yeah. Okay. So, what is the Un? N, the term of Un is right here 1 upon n into n plus 1. Okay. So by partial fraction, so this can be written as 1 upon n minus 1 upon n plus 1. Okay, by partial fraction. So this is very simple. So we make here this sequence of partial sum by definition. So what is the sequence of partial sum? So what is Sn? So what is Sn? Okay, Sn is the partial sum of n terms in this series. So what is un is this? Okay, so first term is what? Okay, put n is equal to 1. Put n is equal to 1. So 1 minus 1 upon 2. Okay, plus. Put n is equal to 2. 2. So that is 1 half minus 1/3. Okay, plus and so on. So what is the nth term? So 1 upon n minus 1 upon n plus 1. Okay, so this is the partial sum Sn. So Sn, so this is the addition of first n term in this series. So this is the Sn. So what happened here? So minus half plus half get cancelled. Minus 1/3 plus 1/3 get cancelled. 1 half minus 1 by n minus 1 by get cancelled. So this is 1 minus remaining here 1 upon n plus 1. So this is Sn here. So we find the limit of Sn. So limit of Sn is what? As n tends to infinity is equal to limit of Sn is what here? This. N tends to infinity 1 minus 1 upon n plus 1. Okay, so this is equal to limit as n tends to infinity 1 minus 1 upon n plus 1. So what happened here? So 1 minus as n tends to infinity, this is a tends to 0. Infinity 1 upon infinity 0. So limit is 1 here. Okay, limit is 1. Therefore, this sequence Sn converges to 1. Therefore, the sequence Sn converges to 1 because the limit of Sn is 1. Therefore, the sequence Sn converges to 1. Then by definition 2. Yeah. What happened? Therefore, the series summation 1 upon n into n plus 1 converges to 1 also. Hence the example. So very simple examples. So then next part is this series, convergence of series. So first we take here positive term series. So what is the positive term series? Positive term series. Okay. So it is the definition is very simple here. So in a series, all terms are positive, then the series is called positive term series. A series definition. A series summation un. So this is a notation. Is called a positive term series. Is called a positive terms series if un strictly greater than 0 for all n is equal to 1, 2, 3 and so on. So un greater than 0 means each term of that series is greater than 0 means positive. Okay. So for example, very simple example we take here. So 1 upon n. So this is a series what? 1 plus 1 half. Put n is equal to 1, n is equal to 2, n is equal to 3, 1/3 and so on. 1 upon n plus and so on. So this is the positive series here because each term is greater than 0. So that is each terms is positive. Then the series is called positive series here. Look, summation un be an infinite series, let summation un be an infinite series of positive terms, let Sn be a sequence, Sn be a sequence, let Sn be a sequence of its partial sum, sums. So that is, so what happens? So that is Sn is what? So that is u1 plus u2 plus u3 dot un. Okay, so un minus 1 plus un. Okay, so then what happened? So this is greater than equal to 0. Why? Each term is positive. So this is sum also positive. So this is greater than equal to 0. Yeah. Okay. So what is Sn minus 1? So that is u1 plus u2 plus u3 plus and so on un minus 1. Okay. So therefore Sn minus 1 is equal to what? So this minus this. So all those terms get cancelled. So this sum and this sum get cancelled. Only remaining here un. And this is greater than equal to 0. So this is Sn is greater than equal to Sn minus 1 for all n is equal to 1, 2 and so on. So what it imply? Sn greater than equal to Sn minus 1. So this is the definition of increasing sequence. Therefore, sequence Sn is an increasing sequence. So this is okay, increasing sequence. Okay. So we learn here what is the positive term series. Then what is the geometric, most important, what is the geometric series? Geometric series. Geometric series. Okay. So what is the definition? Simple definition here. So what is the geometric series and what is the convergence of the geometric series? The series. Summation AR raised to n minus 1 is equal to, where n is equal to 1 to infinity. So this is what? This is what here? So this is A into bracket, put r is equal to 1. Okay. Put n is equal to 1. So r raised to 0, that is 1 here. So first term A common out here. Put n is equal to 1. N is equal to 1. R raised to 0. So that is 1. So put r is equal to 2. So this is r plus r square and so on, plus so on, r raised to n and so on. So this is the infinite series here. Okay. So this series is called where a not equal to 0. So this series is called geometric series. Geometric series. Okay. So this series is called geometric series. Okay. So what is the common ratio? So the ratio of two consecutive terms means what here? So r square divided by, so that just what happened here? R divided by 1. Then ratio of consecutive term, r square upon r. So that is and so on. Okay. R raised to n upon r raised to n minus 1. So this is simply r. Okay. And this is called and which is constant, is constant, is constant, and this is called common ratio. Common ratio. Okay, common ratio. Okay. So this is called a geometric ratio series with common ratio R here. So we take theorem, very simple theorem. Theorem. So what is the convergence of geometric series here? Okay. The positive term geometric series, the positive term geometric series summation. So this is Rs to n. So taking A is 1 here. So that is Rs to n. Geometry series Rs to n. N is equal to 1 to infinity. So here taking A is 1. So we write this. This is in this form here. Convergence is convergence for R is greater than 1. Okay. And diverges for R is greater than equal to 1. Okay, so that is the proof here. What is the proof? Okay, proof is what here? So, case 1. Case 1. So if what? Case 1 is what here? If R is less than 1, greater than 0. So first case, R greater than just a minute, R is less than 1 here. R is less than 1. So we take this case. If R is less than 1, then what is the convergence of geometric series? So for the positive geometric series, for the positive series, summation Rs to n, the sequence we find a sequence Sn of partial sum. So Sn is the sequence of partial sum is given by. So what is the series? This is the series here. Summation Rs to n. So what is the partial sum? So this is the sum of. So nth term in Sn is the n term in this sequence Sn. Now what is Sn? So this is sum of first n term in the series. So what happened here? So 1 plus R square plus and so on. Rs to n minus 1. Okay. These are the n terms. So these are the n terms here. So 1, 2, 3 and so on. N terms here. Okay. So what is this? Sum of this series is what? So this is 1 minus this is the formula Rs to n divided by 1 minus R. 1 minus R. Okay. 1 minus R. Okay. 1 minus Rs to n divided by 1 minus R. So this can be written as dividing 1 minus R to 1. So 1 minus R minus Rs to n divided by 1 minus R. And this is always less than 1 upon 1 minus R. Less than. Trivially, this part is greater than this. This part is greater than this. Okay. Then this minus this is less than 1 upon greater than, I think, we don't know, greater or smaller. But this minus something is certainly less than this. We don't know. So this is greater. It depends on the value of R here. Okay. So this minus this is less than trivially 1 upon 1 minus R. So Sn is less than 1 upon 1 minus R for all n is equal to 1, 2, 3 and so on. Okay. So what happened here? Sn is less than 1 upon 1 minus r. Then what happened? So therefore, sequence Sn. So all terms of the sequence less than some real number. So this is upper bound. Then the sequence Sn is bounded above. Therefore, the sequence is bounded above. And we see here the positive term series is increasing sequence. Okay, positive term series is increasing sequence, and which is also bounded above. Then by theorem, therefore this sequence Sn is convergent. Okay, therefore sequence Sn is convergent. Therefore, the series, if Sn is convergent, then the series sequence Sn is convergent, then the series Rs to n is convergent when R is less than 1. So case first one is proved here. What is the case 2? Case 2. Okay. Case 2 is what? For R is equal to 1. R is equal to 1. Then what is Sn? Put R is equal to 1. Sn is, put R is equal to 1. 1. So 1 plus 1 plus 1 plus and so on n times. So this is n. So limit of Sn as n tends to infinity. So that is the limit of n as n tends to infinity. So this is infinity. N tends to n. Therefore, Sn diverges to infinity. And if the sequence diverges to infinity, therefore Rs to n, the series, diverges to infinity also. Okay? So is equal to the proof R is equal to 1, then the theorem is proved here. So what is the case 3? Case 3 is what here? R is strictly greater than 1. R is strictly greater than 1. So what is Sn? Sn is what? Sn is what? This 1 plus R square plus and so on Rs to n minus 1. Okay. So what is the partial sum? So we know that the partial sum is 1 minus Rs to n divided by 1 minus R. Yeah. Okay. So this can be written as, so Rs to n minus 1 divided by R minus 1. Taking limit of this. So the limit as n tends to infinity of Sn. So this is what? Limit as n tends to infinity. Rs to n minus 1 divided by R minus 1. So that is infinity. Why infinity? Because R is greater than 1. R is greater than 1. Then it's the power. And n tends to infinity. So this is equal to infinity. Therefore, Sn, the sequence Sn, diverges to infinity. Therefore, the series Rs to n also diverges to infinity. So we prove here the series, geometric series Rs to n converges if R is less than 1 and diverges if R is equal to 1 and R greater than equal to 1. Hence the proof of the theorem. Okay. So we remember that the geometric series, what is the definition of geometric series and what is the convergence of the geometric series. Okay. If R is less than 1, the series is convergent, and if R greater than equal to 1, then the series is divergent. Okay. So this is the convergence and divergence of the geometric series. We take a theorem. So tomorrow we discuss about P series here, and taking examples on geometric series and taking examples on P series and so on. So we stop here. Thank you. Okay.